Welcome, ladies and gentlemen. May I have your attention, please? Thank you. My name is Mr. Fritz, and I look forward to getting to know those new faces in here. We're going to have a great semester in advanced algebra. There's some things that are going to be the same as your previous advanced algebra teacher. There's some things that are going to be different, and we're going to talk about those over the course of the next couple of days. But first, let's get right to it. So we need to be comfortable multiplying, right? Multiplying variable expressions together. Today, as we investigate quadratic functions, right? We've got a couple different content objectives, but both of them are going to hinge on our ability of handling these quadratic expressions and manipulating those variables. And so let's make sure that we're comfortable simplifying these expressions. We know back from middle school that if we have an outside factor like 5k, right, multiplying some binomial polynomial, in this case 3 minus 4k, we can simply use the distributive property and go term by term. So we grab onto the outside factor 5k and distribute it through the parentheses term by term using multiplication. So this one's easy cheesy. We get 15k and then minus 20k squared. Go ahead and raise your hand if you already had that. So who already had that for number one? Great. We can also multiply two binomials together. All right. And we can do that kind of by a double distributive property process, also called the FOIL method. We talked about the FOIL method last unit. And so if we did 2x times 2x, that would be 4x squared. That would be like the product of the first terms in each binomial. And then if we did 2x times the negative 3, right, that would be the outside product, and that would be negative 6x. So that would be like the O in FOIL. And then if we did positive 3 times 2x would be plus 6x. That would be the inside product, or the inner product, and that would be the I in FOIL. And then you guessed it, the L is for last, right? The product of the last terms in each binomial would be positive 3 times negative 3 would be minus 9, that would be L. So everybody can see it, F-O-I-L, there's my FOIL process. And that's just my mnemonic, my memory device, in order to remember how to multiply two binomials together. But this isn't standard form, right? In order to be standard form, we want it fully simplified and any like terms combined. And so go ahead and share with the class a pair of like terms when I call on you. So what's one pair of like terms that I could combine through addition and subtraction? Lucas?
The negative 6x and 6x.
Absolutely. Both of those linear terms, thank you, Lucas, right, are x to the first, so I could combine them through addition and subtraction and write a single term. It looks like 4x squared minus 9 will be my final answer. Please raise your hand if you already had that for number 2. So who already had that? Yes, awesome, thanks. Number 6 is also a FOIL problem. It's a FOIL problem in disguise. Right now, 4x minus 5 quantity squared means 4x minus 5 times itself, 4x minus 5. So I still rewrite this. I still rewrite this as two binomials multiplied together, just like number 2, right? It's still a FOIL problem, just like number 2. Do not distribute this exponent through the parentheses. We can't do that if there's addition or subtraction inside. In this case, there's subtraction, so we're not going to distribute that exponent through the parentheses, right? We can't do that. Instead, we can multiply 4x minus 5 times itself, 4x minus 5, and do a FOIL problem just like number 2. Let's go ahead and do that. I'll use the same colors from above. My first product would be 4x times 4x is 16x squared. My outside product in red would be 4x times minus 5 is negative 20x. My inside product in green would be negative 5 times 4x is another negative 20x. And lastly, my negative 5 times negative 5 is plus 25. Again, we have like terms. So before we do standard form, let's identify those, right? Where are our like terms going to be here, Coley?
The two negative 20x.
Absolutely, thank you. Those two linear terms, negative 20x, are like terms. Negative 20x plus another negative 20x is negative 40x. So when we're combining like terms through addition and subtraction, the variable component does not change. We don't change exponents, right? We just change how many of them there are. Awesome. Raise your hand if you already had number 3. So go ahead, number 3. Great work. Thanks, you guys. All right, let's consider now solving quadratic equations, and we did this back in Unit 1. In order to solve a quadratic equation, we could consider our forward steps and then reverse and undo those in order to get our solving steps. As we look at number 4, I see that there's only one x term, right? There's only one x term, and it's not in the bottom of a fraction. So I'm ready to cover up that equation and consider my forward steps. If I were to plug in something like in middle school, if I were to plug in something for x and evaluate, the first thing I would do is square it, and then I would subtract 9. So to reverse and undo those, to get my solving steps, I'll simply start at the tail end. If the last thing I did was subtract 9, the first thing I'll do is add 9. To undo squaring, I consider the positive and negative square root. And remember, when we undo even integer exponent, we have to consider two different solutions, right? Two different solutions. So let's see how that looks. First, let's add 9 to both sides for my solving steps. So I get x squared equals 25, and then we'll go ahead and undo, right? We'll undo that squaring by considering the positive and negative square root. And I'm just saying that x is there for some quantity, right? You're doing the positive and negative square root of some quantity. I'll erase it for now on. If x squared equals 25, then x is given by the positive and negative square root of 25. And that may reduce, it may not, but either way, it'll break into two separate branches. So I know that x is given by the positive square root of 25. In this case, it does reduce to 5. And x is given by the negative square root of 25. That's negative 5. Moment of truth. Raise your hand if you had both solutions. Both solutions for number 4. The two answers, x equals 5 and negative 5. Way to go, you guys. That's awesome. Great work. Let's go ahead and take a look at our final solving equation, number 5. And this is x minus 9 squared equals 16. Did we already do this one? Did we already do this? No, we did x squared minus 9 equals 16, which is distinctly different than x minus 9 quantity squared equals 16. Again, we could get our solving recipe by covering up our equation and considering my forward steps. This time, if I were to plug in a variable value for x and evaluate the left-hand side like in middle school, my first step would be subtract 9. And so this time, my first forward step is subtract 9, then square it, or raise to the second power. Right? So that's going to be a distinctly different recipe for solving when I go backwards. Now the first thing I want to reverse and undo, I want to undo squaring. Well, what undoes squaring? Square rooting. So long as I consider both the positive and negative square root to undo that even integer exponent. And lastly, I'll undo subtraction by 9 by addition by 9. So let's go ahead and apply those solving steps. Here we go. Take the positive and negative square root. That's my first solving step. So we'll go ahead and get rid of the squaring by considering the positive and negative square root of whatever was there. In this case, 16. Sometimes that'll reduce, sometimes it won't, but either way, I'll be able to break it up. Now we can see where the two separate paths are coming by. On the left, x minus 9 is equal to the positive square root of 16. That's 4. On the right, x minus 9 is equal to the negative square root of 16. Oh, I'm going to go right to negative 4 as well for that. Does everybody see where the two paths are coming from? One is set equal to the positive square root of 16. One is set equal to the negative square root of 16. And now we'll finish it out by our final solving step. We're going to add 9 to both sides. We just do it to both equations. So add 9 to both sides, and I get x equals 4 plus 9. I'm getting 13. And I'm getting negative 4 plus 9 is positive 5. 13 and positive 5. I'm not so sure about that. So before I box those, what could I do, right? What could I do to see that these are indeed solutions? Nathan?
You could substitute them for x and solve.
Absolutely. We could substitute those in for x in my original, right? Evaluate and see if I make a true statement. If I do, then those are actual solutions. So let's check. I'm going to grab this 5 and plug it into my original. I can even use the green forward steps as a means for evaluating. So let's everybody do this together. 5 into x. X minus 9 is negative 4. Negative 4 quantity squared is negative 4 times itself. Negative 4 times negative 4 is positive 16. Is x equals 5 a solution? Yes, so we can box it. We can do the same thing for 13. That's pretty sweet. All right, at this time I want you to raise your hand if you had both x equals 5 and x equals 13. Who had both of those? You guys had them? Way to go, you guys. That's great. If you didn't, it's okay. Go ahead and add them. Remember, when we're solving a squaring equation, the next to the positive 2, that's an positive even integer exponent, you have to be on the lookout for two separate solutions. And that's why number 4 and number 5 each had two solutions. And that's going to be a recurring theme throughout today and the next several days. Awesome. Okay, so today we're going to touch briefly on some expectations in this class, but really we're going to investigate them in more detail as they arise, right, in the first several days together. Like we're going to have our first grading of homework, right, based on both completion and we get an accuracy grading here, right, so you get immediate feedback. We're going to have our first quiz after day 4, right? Already we'll be having our first quiz, and it will include some of the solving that we'll be doing today, some of the graphing, and then some projectile motion applications with the graphing calculator. So a lot of these things we'll see as they arise. Today I just want to briefly point out my signal. May I have your attention, please? All right, I've already used it, and you guys have already done a great job responding. I need you to stop what you're doing, look up at me, and listen to what I have to say, because I'm going to say something important, like give you directions, or bring the class together to share our responses, or change the homework assignment, right? Because we decided not to include number 21, but the purple assignment sheet still has it, or whatever. So when I use my signal, may I have your attention, please? I need you to stop what you're doing, look up at me, and listen to what I have to say. Our tardy sign-in books might be different than the other teachers. If you come in on the side table over here, if you're late and don't have a pass, which might happen, I hope it doesn't happen in this class, but it could, you'll simply come in and you'll sign in here in the pink tardy sign-in book for unexcused. You just sign in, right, your name, the period, the date, and the time in. This is your documentation that you were, in fact, here, you were just late. I've probably already taken attendance at the beginning. You already saw me take attendance today. And when Mr. Gabarsky or Mr. Borowski comes around and pulls you out of class and says, how come you were absent this day, right? You'll say, no, I was just late. In fact, I signed in, and here's your documentation. So make sure you sign in when you're late. If you have a pass, then you're excused, but you still have to sign in for the same reason. I will have already taken care of attendance, so you want to make sure you sign in here, and then don't give me the pass. Please put it in here for your documentation, because I'll be wandering around the room and doing other stuff, and I don't want to lose the pass. You'll put it right in the book where you sign in. Other things we'll touch on in the future. Closure and packing up we'll do briefly. Closure is a very important time. It's where we solidify the day's new learning. You had closure with your first semester advanced algebra teacher. It's very important to me that you're not packed up or on your phone, right? Then closure is our time to write down the big ideas, right? And make sure that we understand what we were supposed to learn from the content objectives for the day before you walk out the door. So closure is an important time to make sure we all have a written response on our slide. And we'll either share those with our partners or share it with the whole class. Sometimes we'll have people come down and write on the whiteboard. So it's important to me that you don't pack up, don't put that stuff away, right? Until after we're done sharing all the closure. And then it's okay to pack up during the last 1 minute of class. I know some of you have to get to art class all the way on the other side, right, of the campus, and you have to go to your locker first, which is over in the science wing. And so some of you have a long way to go to your next class. And I want to be respectful of your time. And so when the last minute if class happens, you can pack up. And then when the bell rings, you're free to go. But please don't pack up before then. Be respectful of our time. Our time together here is important, and I want to maximize our use of class time together. And so even if we finish closure and there's 10 minutes left, hey, that's a great 10 minutes to start on your assignment. Practice right now while you're still in the room. You can still ask me questions. You can ask each other questions and get a start on your assignment before the bell ever rings. The last minute you can pack up for class, but please don't get up and go to the door. That's something that might be different from your first semester advanced algebra teacher. It's important to me that you stay at your seat until the bell rings, and then when the bell rings, then you're free to go. You may pack up. You can get your backpack already and packed up, and that's great. Everything put away. You can check your phone then the last minute, whatever, but please stay by your desk. Don't go to the door. Then when the bell rings, then you'll be able to go and get to where you need to go. We'll talk about extra help. Lots of opportunities for extra help. We've got math resources every single hour except for 4A. 4A is my common planning time with the advanced algebra team, but I could also answer questions you may have if you email me and set up an appointment. That's the best way to contact me if you have questions, is just send an email, because I check my email all the time. Moodle is your one-stop shop for all classroom resources. Right now we're recording our class period right now together, and as an A-day class we'll typically be recording this hour or second hour or both. And so please don't let that be a source of anxiety for you, right? You might end up on the YouTube channel, right? So good for you. But that's a resource for students. Let's say that you had a dentist appointment during 3A. And I know you're saying, Mom, don't make my dentist appointment during advanced algebra class, my favorite class, my favorite teacher. And I can understand that, and I respect that. But it might be the only time that you can get in, so you don't get to go to 3A that day. You miss advanced algebra, that's okay. You're going to go to the Moodle site and you can listen to the class recording. Right? Click on the link for the class recording, and that'll take you right to our YouTube channel on the Advanced Algebra playlist. And you can listen and as if you were here, complete your note sheet. You've also got completed class notes as a PDF. I export our notes as a PDF and post them for completing class notes on the Moodle site as well. There's blank handouts There's worksheets if it's a worksheet assignment. There's a worksheet link as well as the regular book problem schedule, the same as your purple sheet. And then answer keys. If we have worksheets, the answer keys would be posted there too in red. And so your Moodle site or Advanced Algebra is your one-stop shop for everything in the class. And we'll talk about more. Same grading criteria, but I want to make sure that we have time because we're a little crunched during 2A with the new schedule. So let's go ahead and get going. Today we're going to solve quadratic equations and make an explicit connection between the solutions to a quadratic equation and the graph of that quadratic equation. Remember, for middle school, that's called a parabola. And so we're going to make a connection between the graph of a quadratic equation and the solutions to a quadratic equation. We're also going to expand products and squares of binomials, and you guys have already done that in Bellwork. When you multiply those two binomials together for number 2 and number 3, you're already multiplying, right, two binomials together or expanding a square of a binomial. And lastly, we're going to use quadratic expressions to model area problems, and so I'm excited about that. Let's think back to Unit 1 and your favorite game. No, I'm not talking about COD Black Ops 3. I'm talking about function calisthenics. And so remember function calisthenics back in Unit 1 where we stood up and we modeled the behavior of a parabola, y equals x squared. And so let's consider the behavior of our parent function y equals 1x squared. Let's carefully sketch a graph of that parent function on your note sheet, you guys. I'm going to go ahead and do y equals 1x squared. I'm going to do that in red on the smartboard. Let's consider what that would look like if we plugged in the variable value for x 0 and evaluated. I'd get y equals 0. And so 0, 0 is on my parent function. 1 comma 1 squared, so that'd be 1 comma 1. So 1, 1. 2 comma 2 squared would be 4, is that right? So 2 comma 4. 3 comma 3 squared is 9. We'll get one more point that fits on here on that right side of the parabola, and we can do the same for our negatives. Negative 1 quantity squared is positive 1. Negative 2 quantity squared is positive 4. Negative 3 quantity squared is positive 9. Everybody, can you see the bowl shape? Can you see the parabola there? Let's go ahead and connect that in a nice smooth bowl shape. Remember, no corners or kinks. It would be a nice smooth curve. And there's our parent function, our parent quadratic equation, the squaring function, or a parabola, right, as we called it, a parabola. All right, now we're going to consider what happens when we take a multiplier in front of that, y equals 1x squared. What if we change the multiplier in front of that to a 2x squared, or a 1/2 x squared, or a negative number x squared? What's that going to do to your function? What I want you to do is turn to your partner, and when you talk to your partner, I want you to decide what those multipliers are going to do to the graph. And you can do each one individually if you want, right? Or you can do a general description telling us the rules for how that'll change the original red graph. So go ahead and turn to your partner and discuss how that multiplier is going to change the appearance of the graph right now, please. Okay. At this time I asked, did you share with the whole class what you and your partner were talking about for what the effect of this multiplier in front of my x squared does, whether it's 2x squared and 1/2 x squared and negative 3x squared, what effect does that multiplier have on my parent function, that parent function that's in red? So what's that multiplier going to do? Alec and Courtney?
We thought that if it's a greater number, it will get wider, and then if it's a lower number, it will get steeper.
So if it's a greater number, it will get wider like this. And if it's a what number?
A smaller number, then it will get steeper.
And if it's a smaller number, then it'll get steeper. Go ahead and raise your hand if you had the same description as Alec and Courtney. So wider, greater number, wider. So some of you not. Okay, so what about you guys that were not? So what were you guys that didn't think that? What did you guys say for your description? What did you guys say for your description? Lucas?
I just had it flipped around, that the larger the multiplier is, the steeper, and the lower it's going to be wider.
So the lower, okay, so the larger the number, steeper, and then the lower number, the wider. So who had a similar description than Lucas? Yes? Okay, so we've got two different descriptions, and I would agree with the majority. If the number is greater than 1, then every y coordinate is going to be that many times taller. And so if I had y equals 2x squared, guess what? every y-coordinate on my original parabola's arms is going to be twice as tall, which visually is going to make your arms twice as steep. Let's go ahead and see how that'll change the appearance of the graph. I'm going to use blue. For y equals 2x squared, I still have the same vertex coordinate. When I plug in 0 and evaluate, I still get 0 squared is 0 times 2 is 0. But watch what happens when I now plug in 1. 1 squared is 1 times the 2 makes this not 1 comma 1, but 1 comma 2. Look, twice as tall. You guys, twice as tall. 2 comma, not 4, but 2 comma 8. Look at twice as tall. That's not 4 units away from the x-axis for the x-coordinate 2. It's 8 units away from the x-axis for the x-coordinate, right, 2. So it's twice as tall. And if I did 3, I'd get 3 comma, what's twice 9? 18. So I'd be all the way up here. So once again, the multiplier 2 makes my parabola arms twice as tall, and it visually looks twice as steep. Let's go ahead and complete our second function graph. So negative 1 comma 2, negative 2 comma 8. Again, nice and smooth bowl shape. I like to affectionately refer to parabolas as total bowl shape, right? Because they look like the shapes of bowls when we graph them. Y equals 1/2 x squared. Y equals 1/2 x squared. I'll do that in green. Now my multiplier is a number in between 0 and 1. And so the arms are going to be half as tall, right? Those arms are going to be half as steep. In fact, the y-coordinates are going to be half the distance away from the x-axis. So check it out. It's not going to be 1 comma 1. It's going to be 1 comma a half of 1. It's not going to be 2 comma 4. It's going to be 2 comma a half of 4, which is 2. Look at that. So 2 comma 2 is my new integer point. Negative 1 comma 1/2. Negative 2 comma 2. We could continue this on if we wanted to do the y-coordinate that corresponds to x equals 3. It would be half of this red y-coordinate 9. What's half of 9? Half of 9 would be 4.5. Now we're wondering, could we get this simply by evaluating my function rule? Yes, we certainly could. In fact, I could plug in, right? I could plug in 2 into my third equation in green and work from the inside out. I'll square 2 and get 4. I'll take half of 4 and get 2, and I'll plot that point 2 comma 2. But instead of taking the time to make a table of values for each of these and sketch a graph, I wanted instead for you to consider the transformations that occur when we have that multiplier in front. And so that's a time save. All right, let's go ahead and finish it up with our negative 1. Be ready to tell the class what does that negative do to the parabola, to my parent function? What effect does that negative have? Nick?
Flips it upside down.
Absolutely. It flips it upside down. So that negative means opposite orientation. Instead of a right side up parabola, we have an upside down parabola. And the 3 times as steep. Let's put it all together. So we've got upside down and 3 times as steep. So instead of going out 1, up 1, I'm going to go out 1 and down 1, 2, 3. 3 times as much, you guys. Instead of going out 2, up 4, I'm going to go out 2 and down 3 times 4 because of the multiplier of 3. Well, that's all the way off the chart. So I'm all the way down here at negative 2 comma negative 12. Negative 2 comma negative 12. And so you see how much steeper that is? Oh, goodness. You see how much steeper that is, you guys? 3 times as steep and upside down. Awesome. What kinds of questions do you have about our graphs of a parabola? Okay, so what we're going to do next is set up our Unit 6 discussion. In Unit 6, we're talking all about quadratic functions. So what does it mean to be quadratic? It means that our highest degree term in the polynomial is degree 2. It's got a squaring term. It could have a linear term, that is an x to the first term. It could have a constant term, right? That's a +7 or a -13/4, or not. In order to be a quadratic function, we just have to have that x squared term. So a quadratic expression in standard form is ax squared plus bx plus c. If we set that equal to 0, it's a general quadratic equation in standard form. If we called it a function f of x, it would be a general quadratic function, right? And the ax squared term is the quadratic term. It's the squaring term. The bx, the x to the first term, is the linear term, and that comes from, if you graph y equals x to the first, it would be a line, so that's called the linear term. And then lastly, that plus c is just some number without a variable component, like 11/4. That's called the constant term. Let's go ahead and solve several quadratic equations. sketch the graph and then compare the x values of my solutions with the graph. So let's consider the quadratic equation x plus 5 quantity squared minus 4 equals 0. Everyone, if we were, and we're not going to do our forward, reverse, and undo every single time, but we will do this for the first several. If we were to solve this quadratic equation, I first check and see, does x appear more than one time? No. Is x in the bottom of a fraction? No. So I'm all ready to go with my forward steps. Everyone, we could cover up the equation and pretend we were in middle school. If we plugged in a variable value for x and evaluated that expression using our forward steps, the first thing we would do is add 5. And so my first forward step in green would be plus 5. Then I would square it. And lastly, we would subtract 4. So to get my solving step recipe, I'll go ahead and reverse and undo those 4 steps. If my last forward step in evaluation was minus 4, guess what? My first solving step is going to be add 4 to both sides. Then I undo my squaring. We already saw that we undo squaring with square rooting so long as we consider both the positive and negative square root because we're undoing an even integer exponent, that x squared. And lastly, I undo addition by 5 by subtraction by 5. All right, guys, let's go ahead and do it. Our first solving step in red. Add 4 to both sides. Thanks for showing that. So plus 4, plus 4. That gives my quadratic x plus 5 quantity squared. Alone on one side equal to 4. Now we'll go ahead and take the square root of both sides so long as we consider both the positive and negative. And so x plus 5 must be given by the positive and negative square root of whatever was there. Sometimes this will reduce, sometimes it won't, but either way we'll be able to break it up into our 2 separate paths. We've got x plus 5 equals the positive square root of 4. And x plus 5 equals the negative square root of 4. If this had been 5 inside my radical, I would write root 5 here and negative root 5 here and continue going. So it's okay to have radicals in your answer, and you will in some of your homework exercises. But it looks like positive square root of 4 does reduce, and negative square root of 4 does reduce. And we can now finish it out with my final solving step, minus 5 from both sides. So x equals 2 minus 5. Let's see, that would be negative 3. And x equals negative 2 minus 5 would be negative 7. All right, again, before I box this, I can always check by taking this negative 7 and plugging it into my original, following my forward steps and seeing if it makes a true statement. So again, we're not going to do it every single time, but I want to make sure that we have a comfortable, strategy, a procedure in place that we can use to be successful. So here I go, negative 7 into the original. Plug it in for x. Negative 7 plus 5 is negative 2. Then square it. Negative 2 times itself would be negative 2 times negative 2 is positive 4. And then positive 4 minus 4, does that equal question mark 0? Yes, and so we've got a solution to my quadratic equation. And we get the same if we evaluate it with negative 3. All right, guys, now let's go ahead and let this be a function. Bless you. Call it a function y equals x plus 5 quantity squared minus 4. And let's go ahead and sketch a graph of that function by considering x values, plugging them into my function rule, and seeing what y coordinate, what y output they're paired with. So let's go ahead and make a table of values, guys. And let's plug in x values, negative 6, negative 5, negative 4, negative 3. I'm going to do negative 2 also, I think. No, I'm going to do negative 7 also. And if we need more, we can add more, you guys. That's the beauty of having a function rule, is we could evaluate this as many times as we want for as many different x values as we want it to. So I'm going to go ahead and evaluate now with my x values and see what y coordinates is paired with. So when I plug in negative 7, I get negative 7 plus 5 is negative 2. Quantity squared is positive 4 minus 4 is 0. I feel like we just did that. Negative 6. Everybody, let's plug in negative 6 for x and work from the inside out. So here we go. Negative 6 plus 5. Negative 1. Negative 1 quantity squared is positive 1. And positive 1 minus 4 is negative 3. Maybe negative 3. Negative 5, I got this one. Negative 5 plus 5 is 0. 0 squared is 0 still. And then 0 minus 4 is minus 4. Negative 4 plus 5 is 1. Squared is 1. Minus 4 is negative 3. And we're close. Negative 3 plus 5 is 2. 2 squared is 4, and 4 minus 4 is 0. Okay, guys, let's carefully plot those on the xy coordinate plane and see what we're looking at. So when I plot negative 7 comma 0, negative 6 comma negative 3, negative 5 comma negative 4, negative 4 comma negative 3, and negative 3 comma 0, can you begin to see the bowl shape, right, visually? Do you see what that looks like? Let's go ahead and connect those and make a nice smooth parabola. Now we can list those x-intercepts, right? Those x-intercepts as an ordered pair x comma y. So be ready to share with the class when I call on you. I want to know what that x-intercept is as an ordered pair x comma y. Right? What would that be as a point? Austin? Negative 3 comma 0 is an x-intercept of my graph. Good. What would this other x-intercept be? What would this other x-intercept be? Eric? Negative 7 comma 0. Awesome. Thank you. Are there any other x-intercepts of this graph? Are there any other x-intercepts of the graph? No, right? How do we know? Even if I make my window bigger, right? If I zoomed out and I made my x-axis on my graph span out towards negative 100 and positive 100, how am I confident? Why am I confident that there's no other x-intercepts? How do we know there's no other x-intercepts hiding out there? For another day? We'll investigate it in more detail later, right, when we look at polynomial equations of higher degree. But for now, suffice it to say that a parabola, right, a parabola just has one turning point. It's a bowl shape. It's not a squiggle curlicue where it could come back and hit the x-axis again. We've already seen both arms of the parabola, right? And that's it. So even if we zoom out and zoom out and zoom out and zoom out and zoom out, we're never going to have another place where it comes back down and touches the x-axis because we can see both sides of the parabola. We can see both arms. We're going to look at that in more detail in upcoming discussions and units. Let's go ahead and solve a different equation. So once again, if we were to reverse and undo our solving steps, right, we could get a recipe for success. In the interest of time, we're not going to do that now. Instead, we're going to jump right into our inverse operations. Typically, we want to add or subtract, multiply or divide to isolate the quadratic term, and then undo squaring by square rooting. Let's go ahead and do that then right off the bat. Looks like adding 9 to both sides is my best first solving step. That isolates the quadratic term 3x squared equals 9. Dividing both sides by 3, we'll get the x squared alone. So let's go ahead and do that next, please. That'll isolate the x squared, and I get x squared equals 3. And now we can undo squaring by square rooting. So if x squared equals 3, then x must equal the positive and negative square root of 3. Sometimes that will reduce, sometimes it won't, but either way I know it's two separate values. One of them is x equals root 3, and one of them is x equals negative root 3. Does anyone have their calculator handy? Nick, would you go ahead and do root 3 and see what we get about as a decimal?
1.73.
So then negative root 3, right? It would be about negative 1.73. And the reason I'm putting dot, dot, dot there is that this is an irrational number. As a decimal, it's going to go on forever and ever without stopping or falling into a repeating pattern. So I'm just putting that dot, dot, dot there to show the viewer that that goes on forever and ever without stopping. All right. Thank you. Let's go ahead and now make a graph of 3x squared minus 9 equals y, a function rule, where I can create a picture by choosing some x values, evaluating them, and seeing what y coordinate, what output they're paired with. So let's go ahead and consider, I don't know, negative 2, negative 1, 0, 1, 2, and evaluate my function rule. Everybody, let's plug in our variable value x -2 and work from the inside out. And so if I plug in -2 right there for x, let's square it first. So -2 squared is 4. 4 times the 3 in front is 12. 12 minus 9 is 3. Are you guys getting 3? Awesome. Let's keep going. -1 squared is +1. +1 times 3 is 3. 3 minus 9 is -6. So what you guys are getting -6? 0 in for x. 0 squared is 0 times 3 is still 0, and then minus 9 last is -9. 1 in for x. 1 squared is 1 times 3 is 3. 3 minus 9 is -6. 2 squared is 4 times 3 is 12, and then 12 minus 9 last is 3 again. All right, guys, let's go ahead and plot these xy coordinate pairs on our axes and see what it looks like. So -2 comma 3, -1 comma -6, 0 comma -9, 1 comma -6. Do you guys start to see the bowl shape? Can you see the problem? 2 comma 3. Right. If we go ahead and connect those in a nice smooth parabola while it's steep, right? This looks like a steep arm parabola. We still want to make sure that it's smooth. There shouldn't be any corners or jagged edges. So if we were to continue zooming in here, it would still be a flat bowl shape when you zoom in. We're going to do calculating time. There we go. Measure that. So as I said earlier, I export the notes as a PDF file and then attach it to our Moodle notes. And so I'm just not going to be able to let that left arm of the parabola slide, right? Because I'm going to wake up in the middle of the night and I'll be like, oh, I should have erased that left side of the parabola in example number 2 for Unit 6, Day 1. And I won't be able to fall back asleep. So I'm going to go ahead and fix it right now just so that we continue to be PDFable. Totally better. So glad I went back. So glad I went back. All right, guys. What's up now? Well, we want to go ahead and state the x-intercepts of the graph. And so as I look at that picture, right, for my first graph, I had nice integer ordered pairs. Then I have -3 comma 0 and -7 comma 0. Will I have integer x-intercept coordinate pairs in number 2? Do those look like integer x-intercepts? No, they don't, do they? Right? In fact, they look like they cross in between what? -1 and -2. What if, I'm not sure what that is. So I'm going to go ahead and see if we can't use the graphing calculator to get a decimal approximation for where that crosses. So you don't need to check one out right now. I just want to, if you don't have yours with you, right now that's okay. I just want to see where this crosses. So I'm going to go ahead and put in 3x squared minus 9, right? And I'm going to go ahead and see where this crosses. By considering my graph, if I zoom 6, I get the standard viewing window like your graph on your note sheet, -10 to 10 and -10 to 10. If I wanted to see where that crosses, I could use the calculator. I could use the calculator to get that decimal approximation by doing second trace is the calculate menu, and I would select the 0 option. That second option is 0, and the calculator would ask me for a left bound. So I would go to the left side of where I think that x-intercept occurs, press enter. Right bound would say use the arrow key to go to the right of where I think the intercept occurs. So I go to the right of it. And then a guess, I go ahead and go back in between, right? Those left and right bounds and press enter. And voila, the cursor is going to jump on, right, the x value where the y coordinate is 0. And you can even see that. Y equals 0 when x equals -1.732 ... Where have we seen that -1.732 ... You can't see it anywhere now. Where have we seen that -1.73? right? Where was that from? Nick? Absolutely. We've already seen that positive and negative 1.73. That is the square root of 3. So can we list those x-intercepts? We can list those x-intercepts, and we can do it without decimals. What would it be? Negative root 3 comma 0. Do it. And this one looks like 2, but it's positive, right? Root 3 comma 0. Nice. All right, 1 to go. Holy smokes. 8 minus 2 times quantity, x minus 4 all squared. Remember, depending upon your teacher, I think Mr. Aker changes that subtraction sign into a plus and negative. And that makes it easy for us to get our forward steps and ultimately our reverse and undo steps if we want a solving recipe. So while we did not do a recipe for the first two, this one looks a little more complicated. I am going to do my forward steps. So I'll cover up the equation and pretend I was in middle school and plugged in a variable value for x. What would I do to evaluate? Well, my first thing working from the inside out would be subtract 4. So subtract 4, then square it, then times by a negative 2. See how you're multiplying by a negative 2 right here? And lastly, increase its value by 8, so I'm going to do plus 8. All right, guys. The benefit of that is because now we can get a recipe for solving. My last forward step was plus 8. My first solving will be minus 8. I'll undo multiplication by negative 2 by dividing by negative 2. I'll undo squaring by considering the positive and negative square root. And lastly, I'll undo subtraction by 4 by addition by 4. Let's go ahead and do it, you guys. So here we go. First step, minus 8 from both sides. That gets me negative 8 equals negative 2 times quantity, x minus 4 all squared. Second solving step, bam, divide by negative 2. So we'll divide both sides by negative 2. Thanks for showing that. Negative divided by negative is positive, so I get positive 4 equals, and I've got my quadratic, x minus 4 quantity squared alone. Third solving step, take the positive and negative square root. If x minus 4 quantity squared equals 4, then x minus 4 must equal the positive and negative square root of 4. That may or may not reduce, but either way I'll be able to break it up into my two paths. First path is going to be x minus 4 equals positive square root of 4. What? That's positive 2. Second path is x minus 4 equals negative square root of 4. That's negative 2. And last solving step, guys, add 4 to both sides of both equations. So x equals 2 plus 4, I'm getting 6. 6. And x equals negative 2 plus 4 is positive 2. I'll do a quick check. I'll plug in 2 into my original and follow my forward steps. Right? I knew there was a reason we wrote those green steps. Here we go. 2 minus 4 is negative 2. Negative 2 squared is positive 4. Positive 4 times negative 2 is negative 8. Negative 8 plus 8, does that equal question mark 0? Yes, it does. So we found a winner. I want to box that bad boy. And let's go ahead and make our graph. So we've solved algebraically. We've systematically generated my solving step recipe by reversing and undoing my forward steps. Now it's time to make a graph. So here we go. Let's choose x values and evaluate them in my original. So I'll make my table of values. And let's pick, 2, 3, 4, 5, 6, and evaluate my original. So if I plug in 2, we just did that, right? We did 2 minus 4 is negative 2 squared is positive 4 times negative 2 is negative 8 plus 8 is 0. 3 in for x. 3 minus 4 is negative 1. Squared is positive 1 times negative 2 is negative 2 plus 8 is 6. 4 in for x. 4 minus 4 is 0. 0 squared is 0 times negative 2 is still 0 plus 8 is 8. I got 8. 5 minus 4 is 1, squared is 1, times negative 2 is negative 2, plus 8 is 6. And 6 minus 4 is 2, quantity squared is 4, times negative 2 is negative 8, plus 8 is 0. My goodness gracious, we'll plot these and see what we're looking at. 2 comma 0. 3 comma 6. 4 comma 8. 5 comma 6. 6 comma 0. What's going on here? Did I mess up? What's different? What's different about the appearance of this problem than our previous two? What's different about the appearance of this problem? Katie?
It's upside down.
Yeah, it's upside down. What in our equation could have clued us into the fact that this would be upside down without ever making a table of values? Anybody see what gives this away as being an upside down parabola? Why, maybe I should rephrase that. Could we have foreseen that this would be an upside down parabola just by looking at the equation without doing any table of values, without doing any evaluating? What about now? Got it. So what about my original equation could have clued us into the fact that this would be an upside down parabola now that we've made its picture, or almost made its picture. Nathan?
Because you're multiplying -2.
Absolutely. We have not dealt with transformations of my graph, scooting it left or right or anything inside, but this squaring term is multiplied by a -2. And we saw from our warm-up parabolas that when we multiply by a negative, what happened to the graph? Flip, upside down. So this little times -2 is an indicator that we've got an upside down parabola. More about that later, particularly in FST when you guys do a bunch of transformations. So it's pretty sweet. Or it was pretty sweet until I messed up the graph. I'm gonna split the difference and say that's good. Right there. Still PDFable, right? Still PDF. Alright, so let's go ahead and state my x-intercepts as a ordered pair x, comma y. Be ready because I'm going to call on you. So what are my x-intercepts there? I'm going to practice our names too. So what are our x-intercepts there? Izzy? 2 comma 0. Thank you. So 2 comma 0 is one x-intercept, right? What's another x-intercept? Kelsey?
6 comma 0.
6 comma 0. Good. 6 comma 0 is the other x-intercept. Nice job. All right, guys. So big whoop, right? What's the big idea here? Well, what can we say about the solutions to the quadratic equation f of x equals 0 and the x-intercepts of the graph y equals f of x? That is, what can we say about that first picture, right? The first picture and its solutions to the quadratic equation. What can we say about the second quadratic equation, 3x squared minus 9 equals 0, and the graph y equals f of x? And my favorite, that was quite an equation. Take a look at that. What can we say about the solutions to this quadratic equation and the x-intercepts of the graph? All right, go ahead and tell your partner the connection between the solution and the graph, and I'm going to have a partner pair share with the whole group, okay? So go ahead and talk to your partner right now. What's the connection between the solutions and the x-intercepts of the graph? Still getting used to the contact time schedule. Okay, go ahead and share with the whole group then what you and your partner pair discussed. So what did you guys come up with? Sam and Morgan?
That the solution to the equation are the x-intercepts.
The solutions to the equation are the x-intercepts. Raise your hand if you had a similar description. So we had a similar description. The solutions to the quadratic equation are the x-coordinates and the x-intercepts of the graph. Absolutely. So we'll go ahead and state that explicitly. And so the real solutions to the equation set equal to 0 double underline the x values of the x-intercepts of the graph y equals f of x. That's pretty sweet. And so the real solutions to a quadratic equation or any equation f of x set equal to 0 are the x-coordinates of the x-intercepts on the graph. We saw when x equaled plus or minus root 3, guess what? One intercept was root 3 comma 0. The other intercept was negative root 3 comma 0. When my solutions were negative 2 and positive 2, right, I'd have x-intercepts negative 2 comma 0 and positive 2 comma 0. In the future, we'll be able to go backwards if we can find the x-intercepts of the graph, right? We'll be able to go backwards then and be able to state solutions to the equation f of x equals 0. So this works both ways, which is pretty sweet. Awesome. All right, so what I want you to do right now is practice solving the following. We don't have graphs for these, but we're going to go ahead and do it with your partner now. 1, 2, and 3, and we're going to have you share your responses. So what I'm going to do is pause the recording while you guys work with your partner. I want you to talk. It's okay to talk and check with each other. Let's make sure that everybody's understanding, and please show your work. Okay, ladies and gentlemen, so as we practice solving our quadratic equations, depending upon the complexity of our quadratic equation, we may or may not choose to list our forward steps and then reverse undo to get our solving step recipe. For example, in number 1, I'd simply begin by dividing both sides by 4 and then taking the positive negative square root. So you wouldn't have to make your recipe if you recognize. Number 3, it might be useful to go ahead and make your recipe for success, your solving steps based on reversing and doing your forward steps. I'm going to leave that choice to you, right? In Unit 1, we required us to show our forward and solving steps, and now I'm going to let you decide based on the complexity of the problem. Keep in mind in our test or quiz, though, in order to earn partial credit, you'd be expected to show your work, right, in order to earn partial credit. Otherwise, if you have an incorrect answer, right, and I can't see your thought process, then you'd lose any ability to earn partial credit. So let's take a look at the first one. Number 1, after dividing both sides by 4, taking the positive negative square root and reducing, I get x equals 6 and negative 6. Please raise your hand if you had the same answers for number 1. Who had that for number 1? Way to go, you guys. And number 2, again, we divided first to isolate the quadratic, undo the squaring by taking a square root, positive and negative, break up. But we had a after the fact step here. By after the fact, I mean after we took the positive and negative square root and split it up into 2 separate branches, we had to finish it out by subtraction. I got x equals 3 and x equals negative 5. Go ahead and raise your hand if you had x equals 3 and x equals negative 5. Do you have both of those? Way to go, you guys are doing great. And then lastly, the most complex one involved 2 steps after the fact. What? After we broke up the equation into 2 separate paths, we not only had to do a subtraction, but then had to finish up with the division. I got 2 solutions. Raise your hand if you had x equals 1 and negative 7/5. Did anybody get x equals 1 and negative 7/5? You guys are doing great. Way to go. Okay, so the last portion of today's discussion is going to involve squaring and expanding, right, binomials and factors in order to write in standard form. And we're going to do that in the arena of some application area problems. And so remember that our FOIL mnemonic is a memory device for how we multiply together 2 polynomials. And so if I had 2 binomials, rather, a plus b, right, times c minus d, I could rewrite that as a collection of terms where I get the first term by multiplying a times c. My first would be a times c, and that would be ac. So my first term would be the product of the firsts. A times c is ac. My outside, O in FOIL, would be the product of the outermost terms. In this case, that would be a times negative d. I'm going to do this over here, so I've got some space here. I'm going to do that over here, and I'm going to get minus AD. There's my O. Then the I from FOIL stands for inside, right? The product of the innermost terms. So as I look at my inside terms, that would be positive B times positive C is plus BC. There's my I. And lastly, my L for last is definitely lastly. B times negative D is minus BD. Awesome. So everybody see my FOI and L? We don't want to forget that. We want PDFable. So there's my FOIL, right? we're going to use that as you multiply two binomials together. We know how to multiply x plus 2 times x plus 3. We can use our FOIL process to remind us how to do that. So here we go, x times x. My f would be x squared. X times plus 3 is plus 3x. I would be plus 2 times x is plus 2x. And then lastly, plus 2 times plus 3 would be plus 6. But in standard form, I want to make sure that my result is fully simplified. And so what can I do to fully simplify this? Are there any like terms that I can combine through addition or subtraction? Mitchell?
Yeah, 3x and 2x.
3x and 2x, thank you. So we could go ahead and combine like terms before I write my final answer in standard form. I will get x squared plus 5x plus 6. And that's what we box for standard form. Awesome. Go ahead and complete number 2 and number 3 with your partner. You should be comfortable with the FOIL process, and then we'll check our answers. So go ahead and complete these with your partner. I'm going to do them up here, but don't look at me, right? And then when I'm done, we'll check and compare. Since you guys are already good with FOIL, I'm going to go fairly quickly, right? Because you guys know how to do this, we did it all Unit 5. So go, go, go. Okay, ladies and gentlemen, let's come together and check quickly. Remember, we know how to FOIL from Unit 5, and so when we do our first outside, inside, last, we can see our resulting polynomial. Take a look down at number 3 is the one we're going to check together. My outside and inside product are like terms. Even though one of them was an xy term and the other one was a yx term, the variable component matches exactly. It's each x to the first times y to the first, so I can combine and get a like term. A single xy term. So raise your hand if you have 12x squared minus 7xy minus 10y squared. We got that last one, number 3. Awesome. Let's go ahead and do some things with it now. So let's go ahead and model some area problems as our final content objective, you guys. We're going to model some area problems using polynomial expressions. The key here is recognizing that our area problems for rectangles is base times height. So if I can write a variable expression that represents the base in my rectangle, when multiplied by the height of my rectangle, I can get the total overall area. So everybody, let's consider a portrait that's 20 centimeters by 90 centimeters, and a frame around that portrait that's f centimeters wide. Let's write the total area of the portrait and the frame in standard form. So everybody, let's go ahead and sketch a picture of what this picture and frame might look like. I'm going to grab my tools because let's just say that I'm drawing challenged, okay? So I'm going to go ahead and utilize the smartboard tools. That's a nice way of saying I'm not very good at drawing. I'm making drawings. So I'll go ahead and the smart tools make me a better drawer. All right. So can everybody see your portrait and your frame? Let's go ahead and get some values labeled in my picture then. So if my portrait's 20 by 90 centimeters, I'm thinking that that's kind of the picture inside. So if I go to label, I'm thinking that this dimension here, just on the picture, would be 20 centimeters. And then again, just on the picture, would be 90 centimeters tall. But then I have the frame. How many centimeters wide is the frame? Well, it's f, right? It's f centimeters wide. So I'm not going to put in 3 or 4.5. I'm going to put in f. Where would that go? Well, it would go right here. Right? But it would also go right here. And right here. And right here. So if I could write an expression for the total area A, in general of a rectangular shape, it's base B times height H. It's just that my base, right? My base isn't B, it's what, 20? What's the base of my portrait plus frame? Well, no, my portrait is 20. What would be my portrait plus frame? What would be my portrait plus frame? Lucas?
20 plus f squared.
Almost. Sorry, I was going after Lucas and Lucas because we got Lucas squared in here. Hey, 3A's got a Lucas squared. That's cool. Not every class does. Sorry. Lucas with a K.
20 plus 2f.
20 plus 2f, right? 20 plus 2f, 20 plus f squared. What's it going to be? Well, if we have 20 centimeters plus an f on the left-hand side, plus my f on the right-hand side would be like terms, so f plus f would be plus 2f. Okay, good job, you guys. So I'm going to go ahead and write my base, my entire base as 20 plus 2f. Good work, you guys. For my height, I would go ahead and express that as 90 plus 2f. And so my height is going to be 90 plus 2f. Can I write that sideways? I don't know, I'm going to try. Whoa, whoa, whoa. How do you make an F? Like that? Maybe? We're going for it. We're going for it. Alright, so what would my base B be? My base BB would be squared too. My base BB would be 20 plus 2f. Everybody, let's rewrite that. So there's my 20 plus 2f for the base of my rectangle times the height of my rectangle. I'll do that in green. The height of my rectangle is 90 plus 2f. All right, ladies and gentlemen, here's an expression for the total area of portrait plus frame. Is this in standard form? This is not in standard form. It's in factored form. You recognize that with your parentheses multiplying together. That's called factored form, and you did that for the whole last half of Unit 5. You rewrote it in factored form. We want standard form. So what are we going to do? You guessed it, FOIL. So go ahead and multiply out and combine like terms. You guys watch your signs. First, outer, inner, last. Combine like terms. Box it? No, not standard form. In order to be in standard form, right? In standard form, how do we need to arrange this, right? If we're going to be in standard form. Reading?
You have to have 4f squared first.
Absolutely, thank you. That's perfect. We need to have our dominant term, our highest degree term first, and then descending order. Thank you, that's perfect. So my final answer would be 4f squared plus 220f plus 1800. Nice job, you guys. Now we can box it. 50. So we're looking for 150 here. So what would be different if we were writing the area of a square with sides 2a plus b? Well, let's everybody again draw a picture. Because of my drawing challenges, I'm going to go ahead and click my nice pop-up art animation that I've already created. And we now want to write the area of a square. So this is a square with side length 2a plus b. Everybody take a minute and draw that. If 2a plus b is the side length in this square, then side length times side length, right, would be equal to area A. And so I know that area of a square is side length s squared. In this case, it would be 2a plus b squared. Does this equal 4a squared plus b squared? No way, Jose. This is a FOIL problem in disguise. When I take a binomial and square it, the result is always, always, always a trinomial. And we saw that when we expanded our Bellwork. Remember? This is, I still rewrite like this every time. I still rewrite this as 2a plus b times itself. 2a plus b in parentheses. Let's do that, you guys. First, outside, inside, last. While this is not in standard form currently, I can see these components, my FOIL components, as areas in my original figure. What? I can see the area 4a squared. I can see it. Can you see it? Where's my 4a squared? Well, 4a squared came from 2a times 2a. Geometrically, that would be a square that's 2a by 2a. What? Check it out. There's my 4a squared. Where's my 2ab? Where's my 2ab? Well, geometrically, that would be 2a by b units long. That would be 2a times b. That would be here. Isn't there a 2ab? Plus another 2ab? Oh, that's right here. And where the heck is that b squared coming from? Where's that b squared hiding? Well, that b squared would be, geometrically, a square with b side length times b side length would be right here. There's my b squared. That's pretty awesome. That's a geometric argument for why this isn't just 4a squared plus b squared. We can't distribute that through. We'd be missing both of those 2ab's. Which brings me to standard form. My standard form answer would be 4a squared plus 4ab plus b squared. And we can box that bad boy. Okay. We're still getting used to the new schedule with contact time, so what we're going to do now is, because you guys are good at FOILing, right? The binomial square theorem, we're going to gloss right over. Julie made a mistake expanding a binomial. She didn't FOIL it, right? And so you guys are good at that, so we're not going to examine Julie's mistake. Nor are we going to practice FOILing in class. What we are going to do is take a look at this area application, because that's what you'll have to do, right, for some of your homework problems tonight, including reading questions. So everybody, let's consider number 4 together, and then we'll come together for closure. Please refer to the diagram above. If we wanted to write an expression for the area of each region in standard form, we could begin with our rectangular area formula, base times height. So everybody, let's consider the shaded region. If the area of the shaded region is base times height, what's my base? Well, it looks like my base is base x times my height. Bless you, the height of my shaded region looks like 2x plus 1 units. So an expression for the area would simply be x times 2x plus 1, base times height. Everybody see it? Is that in standard form, however? No, that's factored form again. So to get standard form, what do? Well, we'll go ahead and distribute that outside factor through the parentheses and rewrite in standard form. So it looks like 2x squared plus x. That is in standard form. The larger rectangle could also be gained an area expression by multiplying base times height. It's just that my height here could use a little rearranging. This 2 times quantity, 2x plus 1, could be rewritten using the distributive property as 4x plus 2. This will make an easier base times height problem. In this case, base is 5x plus 3. And height is now 4x plus 2. Is that in standard form? No, we've got to do some work there. So let's go ahead and do 5x times 4x, 20x squared. Plus 5x times 2 is plus 10x. Plus 3 times 4x is plus 12x. And chilling on the back side, my last is 3 times 2 is plus 6. One more rewrite, guys, and we'll be standard form for letter B. So it looks like 20x squared plus 22x plus 6 and feeling pretty good about ourselves until letter C. So can we write an expression for the unshaded region based on the diagram in standard form? Yeah, go ahead and tell your partner what you would do to get an expression for the unshaded region of that figure. What portion would be unshaded then?
You would subtract those two and or the shaded rectangle from the two.
Go ahead and share with the class, right, what you do procedurally to get an expression for the unshaded region. Ellen?
You would subtract the shaded rectangle from the larger rectangle.
Got you. So if you took out with the whole large rectangle minus the shaded rectangle, you'd be left with the portion that is unshaded. Absolutely. Good. Thank you, Ellen. Raise your hand if you have the same approach. So who's going to do the same thing? Let's do it. Standard form, go, go, go. So subtract green, larger rectangle. Sorry, minus also green. Shaded region, 2x squared plus x. Keep in mind we can only do like terms, right? We can only combine like terms to addition and subtraction, and then we'll go ahead and share and see if we get the same thing. I'm going to go right to the answer. It's time. We're in hurry up offense mode. Grab it like a rabbit. We got it. So raise your hand if you had 18x squared plus 21x plus 6. Everybody get that already? Yes, you did. Yes. Ladies and gentlemen, we have just time for closure. Please write down. This is a very important time. We need to make sense of our content objectives. So how are the solutions to the quadratic equation f of x equals 0 connected to the graph y equals f of x? Please write down a response. What does FOIL stand for? Be ready to share. I just want true or false for number 3, and you can circle it. Right? You can circle true or false for number 3. And then go ahead and expand and simplify number 4. Don't be surprised if I ask you to share your answer with the whole group. You guys are doing great. How are the solutions to my equation f of x equals 0 representing the graph y equals f of x? Riley?
They're the x-intercepts.
Absolutely. The real solutions are the x-intercepts of the graph. So the solutions are the x-intercepts of the graph. Awesome. What does FOIL stand for? What does FOIL stand for? Morgan? First, outside, inside, last. Awesome. Thank you. True or false? Does m minus 5 quantity squared equals m squared minus 25? Mandy? False. Raise your hand to get false for number 3. False. Good job. And then our fully simplified form. What did you get for fully simplified form at the end of the day? Mitchell?
We have 2x squared plus 11x.
2x squared plus 11x minus 21. Raise your hand if you got the same thing. So our final answer. Way to go, you guys. Strong work today. I'm going to go ahead and stop the recording and save it. You may go ahead and pack up now that it's the last